Hello team, this is going to talk about distributing load. So in MapReduce and other data parallelism paradigms, we split input to achieve parallelism. And one of the things we want when splitting input is to distribute load across the compute instances. And we want to distribute load so each compute instance performs comparable amounts of work. And this is because the total execution time of our program is determined by the longest running instance. So if there's a straggler, like a map instance that's taking 10 times longer to run than other map instances, then this map instance will slow down our whole task. So one common strategy to get more even load distribution is to send equal amounts of input to each compute instance. So for example, if we send one book chapter to each map instance, then the book chapters might have different number of pages and each map instance will do different amounts of work. And if there's a chapter that is like gigantic, then that map instance will be much slower than the other ones. Instead of splitting the book in chapters, it may be better to split the book in lines and then send each line to a different map instance. This would allow for more even load distribution. Although sending equal amounts of input to each compute instance generally helps, it's not guaranteed to work for all tasks. So some tasks, the complexity doesn't correlate directly with data size. Say we're detecting animals in an image. So it may be harder to detect animal in an image if it's camouflaged. Say if there's a chameleon in an image, it might be much harder to detect than detecting a cat. Or if the cat is on the grass, it might be harder to detect compared to the cat being on a bed. And for these applications, we may use a specific load distribution mechanism so that we get more or less the same amount of work on each compute instance. Another thing to consider when splitting input is that we want small data pieces because this makes it easy to distribute load, like we saw in the chapter example. Instead of breaking the book into chapters, we can break the book into lines, and this will allow for more even load distribution. And the other thing we want is meaningful data pieces. So having very small pieces of data may prevent us from doing some computation. Let's take the animal example. So to detect an animal in a picture, we need the whole picture. We can get a small portion of the picture, otherwise we might not have the whole animal and might not be able to detect it. And of course, the map instances should send meaningful data pieces to reduced instances, as that's what the reduced instance will need. So the reduced instance also need meaningful data pieces. In the case of the animal detection, we want to send a complete file name to the reduced instance so that it can build a list of files where that animal appears in. A common approach to map input items to a compute instance is to use a hash function. So a hash function maps an input to a random output. So the hash function has one random output for each input key. So we give it, for example, an image, and it will give us a number. We give it a word, and it will hash the word and give us a number. And every time we give the hash function the same word, it will give us the same number. If we give the same image 2 times to the hash function, we're going to get the same output 2 times as well. A hash function provides a one-to-one mapping between inputs and outputs. And the hash function can be used to distribute load when there are many items. So for each item, we're going to hash it, and then we get a number, and then this number will allow us to, for example, identify which instance should process that item. Let's go through an example. So many words in English start with the letter S. So if we just map all words starting with S to a given instance, that instance might get overloaded just because there are many words with S, so it might have more work to do than other reduced instances. So one thing we can do instead is use the whole word as a key instead of just the first letter. And then if we use the whole word as a key, what we can do is we can hash the word, this will give us a number, and then we can use this number to identify which reduced instance should process that word. So even though English has many words with S, we would still distribute all words starting with S to different reduced instances, and no single reduced instance would receive more load than the other ones. Well, professor, hash functions might be nice, but I can also do this, load balancing using a big table. So I can build a big table where I'm going to map each word to a reduced instance. Well, that works, but using a hash function has advantages. For example, if you use a hash function, you don't need to build the table in the first place, and you don't need to maintain the table. And maintaining this table might be troublesome because you might process different books with different words. So the rows in the table will need to change depending on what text you're going over. So this we get for free if we use a hash function. So we've talked about this, but I want to go over it again. MapReduce incurs overhead, and sibling load in general incurs overhead. So splitting data, merging the result, transmitting data over the network, all of these tasks take time and use resources. So if we have a simple task and a small data set and we run it in MapReduce, it may just take longer to complete than if we ran it on our own computers. And this happens because MapReduce has a lot of infrastructure attached to it. So it will split data, we have to put it in HDFS, and then the whole computation might just become more expensive. So there is a trade-off between the size of the data set we are operating on, the complexity of the computation we want to do, and when these things are large, then it makes more sense to use MapReduce. And this is not specific to MapReduce. If we have a easy task to do, we might just as well use our own computer instead of putting it on big table and shipping it to Google. It will just, be more work for us and it will take longer to run.